Let us look at this problem, which helps us reinforce some of the ideas in processing of signals using LTI systems, as well as ideas in sampling theory, reconstruction theory, and aliasing. So the problem that we are given is we have an input signal x of t that is passed through this anti-aliasing filter, which has a cutoff frequency of 2000 pi. After that, it makes everything 0. Before that 2000 pi, it only induces a constant phase shift for every frequency. And the question is asking that what is the output of this anti-aliasing filter block? And then once that is, the output is sampled, then reconstructed using 1000 Hertz, what is the output of the reconstruction block? So the main thing to focus here is the first, let's look at part A solution. So since the anti-aliasing filter blocks everything above 2000 pi, let's look at the frequencies of in our input signal. It's 250 pi, so it is not blocked. This is 1500 pi, it is not blocked. But this is minus 3000 pi, which is not within minus 2000 pi to 2000 pi. So what is going to happen is that when we have 3 minus e to the minus j 3000 pi t, this is passed through the anti-aliasing filter, the output is going to be 0. So we don't have to worry about that. Now remember that within 2000 pi, the anti-aliasing filter is just simply inducing a phase shift. So if you remember that your Fourier transform expressions, this phase shift means that this anti-aliasing filter for frequencies that are below 2000 pi is simply inducing a phase shift in your input signal. So what is going to happen is that 5 cosine of 250 pi t, when it passes through the anti-aliasing filter, the output is simply going to be shifted by time units of 50, t minus 50. Similarly, when I take 5 sine of 500 pi t and pass it through this anti-aliasing filter, I am again simply going to get the same signal back, but with a with a time shift of 50. Now, if you are wondering why am I dividing the input signal into 3 different, remember that we are doing LTI processing, and if the input is given by summation of 3 signals, I can individually find out their output and then simply add the outputs of these 3 signals to get the total output. Okay, so part A's then solution is simply that the output of the anti-aliasing filter is going to be I input x of t and out comes xa of t, which is simply equal to 5 cosine of 250 pi t minus 50 plus sine of 1500 pi t minus 50. Okay, this completes our part A. Now let's look at part B. So I can simply break down my part B into the following. My part B is effectively saying that I have this input signal xa of t. I am now passing it through a continuous to discrete block, and my sampling frequency is 1000 Hertz. Then I pass it through a discrete to continuous block with the same sampling frequency, or reconstruction frequency is the same. And what is my y of t? Okay. Now, if I want to analyze that, remember that my sampling frequency equals 1000 hertz, or which is equal to 2000 pi radians per second. So the basic Nyquist criterion tells us that all frequencies, since we are doing ideal sampling and reconstruction, all frequencies below 2000 pi divided by 2, so 1/2 of the sampling frequencies, which is equal to sampling frequency divided by 2, which is simply equal to 1000 pi, will be perfectly reconstructed. Now, remember that your sampling system in this setting is a linear system. It's not an LTI system, but it's a linear system. And my input to this sampling system, this sampling and reconstruction block, is 2 frequencies. One of my frequencies is 250 pi. So this should have been, the parenthesis should have been on the other way around. Let me just fix that. It's 250 pi t minus 50. So since this signal has a frequency of 250 pi, technically speaking plus 250 pi and minus 250 pi, it will pass through this sampling and reconstruction block as it is. Okay, so let's write that down, that 5 cosine of 250 pi t minus 50, when we pass it through C to D and D to C, the output is going to be exactly the input, because we are assuming that everything is ideal and Nyquist criterion is not being violated. Okay, but what about the other case? 1500 pi is higher than 1000 pi. So there will be aliasing of frequencies. How do you figure out what the aliasing is going to be? Well, we'll use our periodic repetition expression. So remember that around here we have the impulse sampled signal, that we can write down the impulse sample signal and its Fourier transform. And later you will see that actually the output comes out to be a very simple expression, but let me go through longer process so that you get a sense of how you could actually figure out what the aliased output should be. So the question we are interested in is, since 5 sine of 1500 pi t minus 50 will alias, since 1500 pi is bigger than 1000 pi, what will it alias onto? Okay. To answer this question, I am first going to express this sign expression using the Euler's identity. So I'm going to write 1500 pi t minus 75,000 pi, which is equal to e to the j, so 5 will stay outside, e to the j 1500 pi times e to the j minus 75,000 pi minus e to the minus j 1500 pi times e to the j 75,000 pi over 2j. And now I know what is the Fourier transform of this entire signal. I'm going to express that. So the Fourier transform of this entire sine is, I have an impulse sitting at 1500 pi. Okay. The magnitude of this impulse is, or rather the real, I'm going to include, technically speaking, I shouldn't call it magnitude, but I'll just write, I'll ignore the negative signs. I'll write that magnitude is 5 by 2 times pi. Okay, that's the, and the phase of this is equal to minus 75,000 pi minus pi by 2, where this minus pi by 2 is, remember that 1 over j is simply equal to e to the minus j pi by 2. Okay, this magnitude is actually, I shouldn't have 2 there, this should be 5 pi. Okay, so this is, if you remember your Fourier transform expressions, remember that e to the j omega naught t, the Fourier transform of that is 2 pi delta of omega minus omega naught. So I'm using that, and that's why the 2 is not there anymore. And over here, since I want to make elaborate a point, I am actually going to have an impulse with a sort of a negative area. I'm going to still call the magnitude, I'm still going to call this magnitude, even though I am actually really talking about just the real valued part. I am not, I am including negative part, so I am really abusing the terminology, but this will be minus 5 pi because of this negative sign, and the phase is equal to 75,000 pi minus pi by 2. Okay. This is the Fourier transform of this 5 of sine 1500 pi t minus 75,000 pi. Now I want to figure out what does this thing alias onto. To figure that out, I am actually going to write multiple copies of this. I'm going to repeat that, if you remember your impulse sampled expression, and I'm going to scale it by 1 over t. So just a reminder that what we are calling impulse sample signals. So if we have gp of j omega, the Fourier transform of the impulse sample signal, that is 1 over t summation k from minus infinity to infinity g of j omega minus 2 pi over tk. So we get multiple copies of our original Fourier transform separated by multiples of my sampling frequency, and everything is scaled by 1 over t. So now I am going to basically, this is my, so I'm calling now this thing as my g of, so the Fourier transform of this, this thing is, I'm calling g of j omega. Okay. And I'm trying to write the impulse sample version of this because I want to explicitly see how aliasing is happening, so that I can then take the reconstruction using an ideal low-pass filter and figure out what the outcome will be. And as I said earlier, if you really go through it, at the end we'll see that the expression is very simple. But I want to go through this longer route so that you can see how it came about. So this is our frequency line, omega. Of course, the first copy we are going to get is exactly going to be the same thing. So I will have one impulse at 1500 pi and another impulse at minus 1500 pi, which I didn't write clearly earlier. So this is going to be at minus 1500 pi. Okay. The magnitude of this is 5 pi and the phase is minus 75,000 pi minus pi by 2, where minus pi by 2 is due to 1 over j. Similarly, the magnitude here is minus 5 pi and the phase is 75,000 pi minus pi by 2. Okay, so this is due to k equals 0. Now, for k equal to 1, I am sitting over here. This is going to be k equal to 1. This version will now be centered at 2000 pi. And when I do that, I am going to get this thing over here will sit over at 2000 minus 1500, which will be 500 pi. Okay. So at 500 pi, I'm going to get a magnitude of minus 5 pi and phase of 75,000 pi minus pi by 2. And of course, I will have a positive version of this at 2000 pi plus 1500 pi, which is 3500 pi, and the phase of this will be the magnitude will be 5 pi. Actually, the magnitude will be 5 pi over t. Similarly, it will be minus 5 pi over t. But of course, the scaling is not going to change the phase. The phases will be minus 75,000 pi minus pi by 2. Now let's look at k equal to minus 1. So k equal to minus 1, we will have at minus 2000 pi, a copy at k equal to minus 1. And this entire blue version will now be centered at around minus 2000 pi, which means that I will have minus 2000 plus 15,000, I will have at 500 pi. Five pi over t, and the phase will be equal to minus 75,000 pi minus pi by t, pi by 2. I should have t's over here also, which I missed that. The reason I'm forgetting them is because at the end of the day, these t's will cancel and they will have no effect. So I want to just not worry too much about them. And then I'll have a negative version at minus 3500 pi. Okay. With the phase of magnitude of minus 5 pi by t and phase of 75,000 pi minus pi by 2. Okay. Now these things are of course going to, this repetition will keep on happening for k equal to 2, k equal to minus 2, and so forth. The main thing to note here is that when you sample when you reconstruct using an ideal reconstruction filter, the ideal reconstruction filter is going to be limited to between 1000 pi, between minus 1000 pi and 1000 pi. It's going to be limited to 1/2 of the sampling frequency. So the ideal reconstruction filter is going to be sitting over here. This is minus 500 pi. Okay. So the ideal reconstruction filter is going to basically block everything outside the minus 1000 pi to 1000 pi region, and it's going to scale everything within this region by, so reconstruction scaling will be equal to by t. So now you can see what will happen, that all of these other copies that are outside the minus 1000 pi to 1000 pi range, they will be blocked. So what will happen is that we will lose all of this region because we have filtered that out through the reconstruction filter. The only thing we will be left with is this green impulse and this red impulse, and the scaling will be by a factor of t, which will basically get rid of this 1 over t here and 1 over t over here. So once gp of j omega is passed through the reconstruction filter, what we get is that the output is simply going to be, we will have an impulse over here and an impulse over at minus 500 pi, at 500 pi, and the magnitude will be minus 5 pi and phase will be 75,000 pi minus pi by 2. Similarly, magnitude here will be 5 pi and phase will be equal to minus 75,000 pi minus pi by 2. So this is basically the whole point is that once this 5 sine 1500 pi t minus 75,000 pi is passed through a sampling system, which is sampling at 2000 pi radians per second, you will have aliasing, and the aliased signal will have, this will be the Fourier transform of the aliased output. So the question is, what is this signal in time domain? So in time domain, you can simply read that out using again the expression. So the time domain aliased output is, I have, let me call that y s of t, which is the output due to the sine. This is going to be, first of all, 5 due to minus 5 due to the magnitude here, okay, and then it's going to be e to the j 500 pi t plus 75,000 pi divided by 2j. Okay, this is due to this positive frequency at 500 pi. Plus, I'm going to get 5 due to this negative frequency, e to the minus j 500 pi. Okay. And plus 75,000 pi divided by 2j. If you are again worried how I got this, remember that I am simply using this relationship which connects complex sinusoid to its Fourier transform. So this is what the expression will be. Let's stick the t here, which I forgot. So this is equal to, if I take the negative 5 common, I'm going to end up with e to the j 500 pi t plus 75,000 pi minus e to the minus j 500 pi t plus 75,000 pi over 2j, and that is equal to sine. So I get sine of 500 pi t plus 75,000 pi, which I'm going to simplify that further. 500 pi t plus 50. So you notice that the 1500 pi frequency, so input frequency, was equal to 1500 pi. After aliasing, we got 500 pi frequency, because the 1500 pi got folded onto 500 pi. Now, to find out what exactly the new time shift and the new value, the new sign should be in front of sine, we had to go through this entire exercise. But an easier way could have been that we could have seen, once you become expert at that, that you could have seen that 5 sine 1500 pi t minus 75,000 pi actually gets alias to 5 sine of minus 500 pi t minus 75,000 pi. Okay. Now, why does this negative sign come about? It is because if you look at this picture, right, this green arrow that goes up here, we have change of basically signs, flipping of signs, because of the fact that the Fourier transform in this case is not symmetric around 0. If this was a cosine, things will be actually much simpler. So at the end of the day, we get these two expressions. So the output will be output y of t. Now we just add the two things. So we get output y of t is equal to, for the cosine case, if you remember, when we had the cosine, we got back the cosine, and we only had the aliasing due to the sine. So we get 5 cosine of 250 pi t minus 50. That came out as it is. But the next signal got aliased. I got minus 5 sine 500 pi t plus 50. Okay, and this is the end of your problem.